As most of you know, beryl is an ore of the mineral of the element beryllium used in alloying with other minerals to give them strength. And just for a little bit of a beryl tidbit here, the largest known mineral crystal in the world is a beryl. It was found in Malagasy Republic. It was 18 meters long and 3.5 meters in diameter and estimated to weigh, get this now, 380,000 kilograms. That is a heck of a crystal, and I don't think it would fit in my house. The beryl family of gems is unique in that it has many of the largest crystals in the gem kingdom. And so that is quite unusual because most gem crystals for the record are small. And so seeing a large stone of over 100 carats in some species would be extremely unusual. So beryls come in a number of colors, and we're going to be talking about this shortly. But the colorless variety is called goshenite. The golden to amber color is heliodor. Pale blue to greenish blue aquamarine. And the largest known cut aquamarine is called the Dom Pedro. It has been on display at the Smithsonian in all but its 10,363 carat glory. Pink to peach colors are called morganite. Excuse me. And it can be found in crystals up to 22 pounds. And the Smithsonian owns a 236 and a 256 carat morganite in their collection. Now, there's some controversy about the raspberry color of beryl, was called pazotite. I don't know if it's still considered to be a beryl. Some people say no. And finally, last but not least, red beryl or bixbyite. And I looked online, and according to Gem A, is to be so valuable that a 2-carat clean bixbyite would be as valuable as a 40-carat diamond. And the largest known one, and you can correct me on this later, Seth, is supposed to be 8 carats. So I don't know if that's 8 carats clean or just 8 carats. So this is a very interesting and colorful family of gems. And I'm hoping that we're going to learn a lot more about them today for some of you.
Just a quick correction there. It's bixbyite, not bixbyite, which is something
I'm
different.
sorry, that's just like one of my little spoonerisms. Bixbyte. I got to get a hold of that. So, we're still way down in numbers. I guess what's going to happen is we're waiting for Mike Wise. I don't know what's going to happen because of the screw up on Zoom. He may not even be coming here for an hour, and I hope that's not true, because he was supposed to be giving us our introduction on the geology of beryls in their pegmatite locations. But that will move the next speaker forward to the beginning. And our next speaker has been a guest of this program before, and his name is Dr. Clement Schwartzinger, and he basically is an associate professor, and I hope I've got this correct, at the Center for Scientific Gemology at Johannes Kepler University, Linz. He not only is a scientist and an academic, but he's also one heck of a good faceter, and has been given the designation of Grand Master of Faceting by the American Gemological Association, AGTA. And because he's a faceter, it means he has a far more intimate knowledge of gems than those of us who just stick them in pieces or talk about them or put them in our collections. So he knows these gems from the bottom up, and I really welcome his knowledge to be shared with us today. So please, if you would just mute your microphones, and welcome Dr. Clement Schwartzinger. Did I say that right?
Thank you for the introduction, Ray, and sorry for a lot of confusing that maybe I also have been giving my part to, because we just changed to summertime this morning, and the correct starting time, in my opinion, would be just in 1 hour. I just see that Peter already arrived here. Wonderful.
Yeah.
At least a couple of us are here. And Peter, just for you, I'm wearing a shirt you should know some minerals on. This is part of Peter's collection. So
just a minute, Clemens. I'm going to ask everybody to go to view in the far right-hand corner and hit speaker view. And that'll give our speaker the center position on the screen.
Okay, Julian, if you could allow me to share my presentation. Yeah, that's wonderful. Oh, just went away. Sorry, not closing. Here, so can everybody see the presentation now?
Not yet.
Not yet. Okay, I'm seeing it. Let me see. Zoom. Trying here.
There we go. There we go.
And
We're almost there.
now it looks like.
Yep.
Yes, so Ray already introduced us to the gem family of barrels, and you know it can grow monster crystals. Here just a couple of smaller ones, from a couple of 2 or 3 carats up to the one in the back is 60 carats, but still you can find huge and enormous gems cut in the barrel family, because it grows in pegmatites, and we will have a talk on pegmatites and the growing of barrels. So I don't want to spend too much time on this. I just want to rush you through some chemical backgrounds and some common places where you can find barrels, and just a couple of nice pictures to introduce you. Of course, we need some science, and you know, the barrel belongs to silicates, and the silicates can be separated in a couple of classes. And the class that we're in is the cyclosilicates, which means there's these silicon oxygen tetrahedrons. They form cycles, and these cycles can have different diameters. And here is the structure that we look at in the barrel. I have very often people hearing referring these structures to peanut-like, as we have channels here. So these channels are perpendicular to the z-axis. We're looking down through the top of a crystal here, and we have this aluminum, the silicon, and the beryllium, all the points here in the corners are the oxygens that are linking everything together, and they form these cycles here. And these cycles are very important in the barrels because they form hollow tubes, and in these hollow tubes a lot of elements or ions can be trapped. Most important, these are water molecules. They can run either perpendicular or in the same direction as the channels. And we have a lot of alkali ions like cesium, sodium, lithium, and even a couple of rarer materials. So you see here the basic cell is looking like this. And if you attach 3 of these together, you can see where the hexagonal structure comes from. Beryllium aluminum silicate is the formula of the ideal, I would call, gaussianite crystal. It has a Mohs hardness of 7.5 to 8, which makes it a very interesting mineral in terms of gems, because it is harder than quartz. Therefore, it does not get scratched too easy, and you can use it for everyday jewelry. The density is 2.8, and refractive index, which is for us gem cutters the most important number that we have to deal with, is 1.56. What does it mean? We have diamond, which has a refractive index of 2.4, which is very, very high. And we have glass, which is about 1.52, 1.55. So it's almost the same refractive index than glass. And it means we have to have a very, very steep angle in order to have light reflecting within the gem and to come back through the table. If you had a diamond, you can go to flat angles. If you have barrels and anything which has a low refractive index, you have to use steeper angles. And typically you do not get the fire because there's no birefringence like in diamond. Crystal structure, as I said, is hexagonal. And in most of the crystals, here's some from my collection, you can really see these hexagonal features. It depends a little bit on, I would just say, the color, which form the barrels are forming. We have the yellowish and blue ones, which are nice pencils. And we have the orange ones, for example, which typically are tabular forms. So something that is also to be considered in many gems is dichroism. However, in aquamarine, which is the most important barrel member, without including the emerald, of course, you typically don't see a lot of dichroism. But here's a nice dark blue aquamarine from Vietnam, and I'll show you just what happens when I turn it 90 degrees in front of a computer screen, which is a polarized light source. So you see, you can differentiate between the E and the O ray, which are the two rays perpendicular to each other, and one is dark blue and one is light blue. This is of course interesting for you if you want to make photos, for example, of your barrels, or if you want to cut them, because if you want to cut them and get the best of color, which is typically the darkest color, you have to orient the material right. So let's talk about the reasons why we have these different colors and these different, I use the word species, I don't know a better word in my English vocabulary. So we have the absolutely colorless variety, which is goshenite. Goshenite, also like morganite, typically has the tabular thin crystals, and the color is due to nothing. So they're typically pure, or they have some ions inside which do not produce any color. The aquamarine, its nice bluish green color, is due to iron, and iron can have either bivalent or trivalent states. So you can have an oxidation number which is 2 or 3. These, especially the bivalent iron, produces the blue color, whereas iron 3 is typically producing yellow colors. If you have iron chloride, for example, you have the iron 2 chloride, which is a bluish green, and the iron 3 chloride, which is intense yellow. So you also need a lower amount of iron 3, and also depends where in the crystal lattice this iron is sitting to make this color. Heliodor is called the yellow variety, and it is typically has some sort of iron inside, mostly of course the trivalent iron, and it is due to natural irradiation that we have some color centers. And color centers is this what makes living very, very hard for us chemists, because it's not a chemical reason for color, it's a physical reason for color. You have your crystal lattice, and if you just knock one of the atoms out of position, it's best researched and easiest explained in diamond, then you produce color centers, and these color centers can be extremely potent and give you a very strong coloration, as it is the case here in heliodors. Morganite, which is the pinkish peach, sometimes orangey variety, has its color due to manganese, and roughly a concentration of 200 to 500 ppm, whereas the red beryl or big spite, if I did get it right, sorry for anything that I'm pronouncing here wrong, is the dark red variety, which is, to my knowledge, almost exclusively found in Utah, and it has a concentration of about 4 to 5 times higher in manganese than morganite. Emerald, just to name it here, has its color due to chromium and vanadium, and even here you have lots of ongoing discussions. Is an emerald if it's green but doesn't contain chromium, or if it's green and it doesn't contain vanadium, or does it have to contain both or nothing at all? The trade is a little bit a problem here for us scientists. If you all could call them barrels and assign different color names, that would be great. A very rare variety is Vorobievite or roasterite, which is a bluish, little bit purplish variety of beryl, and the color is also, or not only the color, but the distinction is that it has a very high concentration of cesium, and it is found in Pakistan mainly, and has some bladed, more or less, crystals. So speaking of pesotite, the information that I got is it's not a beryl, because it is not hexagonal, it's trigonal. And it was assigned a different mineral species already a couple of years ago. So don't talk about this here anymore. So being a cutter, of course, I want to show you a little bit on the process of cutting gems in general, but especially here on a nice beryl. As I told you, the barrel's refractive index is pretty low, so you do not get a lot of reflections and shiny. You have to play a little bit with designs if you want to have something different than just a standard emerald cut, which gives you a color, and yes, that's it. So I always want to have some reflections and some pattern that can be seen if the stone faces up perfectly, and this is the idea that we have. I had a nice 50 carat piece of I would call it aquamarine. It has some light bluish green color. Obtained this from Steve Julatovsky from New Era Gems, and it's probably from from Mozambique. So the first is you have to rotate the stone in your hands, and you have to look at all the different angles and look where you can find a spot which gives you the cleanest and largest stone. I always go for the cleanest and for the best performance. I know a lot of people who go for highest weight, which kills, of course, the optical performance. So then you have to find out the design. In this case, I used the hexagonal design, a couple of unusual, pretty narrow facets, which give hopefully a good light reflection. You see here, this is indicated by using a piece of aluminum to cut over the facets, which leaves these nice marks, and therefore the cut becomes easily visible. You have to do this on both sides, do a lot of polishing, and at the end, you hopefully end up with a gem like this. So from the 50 carats, I could save 14.5 carats. This is also a nice number. If you buy a rough stone and go to a cutter, something in the area of 30% will be this average yield. Of course, it depends on the shape. If it's better shaped, you get 50. In the best of all cases, typically 40%, and sometimes you have to live with 20 to 25% if you want to have precision cutting. Like here we have the focus on the optical image and not on the weight. Yeah, start with some photos of the different species here with aquamarine. I tried to list up the localities that are most interesting for both, for the mineral collectors as well as for the gem collectors. And in aquamarine, of course, we have to start with Pakistan and Brazil. Brazil is the one that's longer known. Pakistan is the one producing extreme amounts in the last 2 decades or maybe 3 decades. And here you see a nice example. They produce very lightly colored, slender crystals. Brazil typically has larger crystals, and they also have the deeper blue. Very famous is the Santa Maria blue, which is a very, very dark blue, which resembles a little bit the one that you can see here down right. Next crystal here is also from Pakistan, but not from Shiga, like most of these crystals come from. This is from Haramosh. This is very dark for Pakistani material, but the one to the right is one of the darkest colors typically produced by a country, and this is from Vietnam. Vietnam and Nigeria, they both produce really nice dark colors. So we have Nigeria, Mozambique, Madagascar. Namibia is also listed here. Namibia produces wonderful mineral specimens. However, in terms of gem cutting, you always have inclusions, or most likely you have inclusions in your stones. They have really nice colors. There have been 2 different finds since 2019 of dark blue aquamarine, but still the clarity cannot be compared to the classical material from Brazil or for example, Pakistan. Vietnam, I have listed, of course, here because of the dark blue colors, and China. China is a huge country, and you can find everything in China. And if it has not yet been found, there's still the time to come that you can find everything in China. China is in that kind a little bit special because the aquamarines that I know, which are originating from China, are not slender crystals, but they have tabular forms. Mount Bue Dong or whatever it is produced has typically dark, medium blue aquamarines that look a little bit like morganite to me. At the bottom, you can see a couple of stones from my collection, and except for the second one from the left, which is from Namibia, everything else is from Nigeria, just to show you the color that is possible to obtain in aquamarines. You have these intensely blue yellowish, you have grayish, medium dark blue, going down to what they call double blue. So what is called Santa Maria Africana, which is not the original Santa Maria, but they have the same color. And in Nigeria, they call this material double blue material. And this is really, if you see the stone in person, you would not think of it to be an aquamarine. Heliodor, the name comes from the Greek god of sun, and it's usually described in this strong yellowish orange, a little bit to greenish color. And the most important deposits are the Ukraine, which I'm sure Peter will show us some nice examples from, and of course some samples from Brazil. We have here Volodarsk, Heliodor, one from Padre Paraíso in the Ukraine, and this is my largest gem example that I have. This is a 5-kilogram crystal, also hailing from Brazil. Here in the top row, you can see Volodarsk, Brazil, and this one is special, and I'm sure we can start a discussion afterwards on this. This crystal was bought with the origin of Tajikistan. And Tajikistan is a very special location that I will come to at the end. And you can think about it either way. There are people who say, yes, I have proved the material is not real, it's a fake. And there are people saying, I have it from the directly mine owner's brother, sister, and so on. A lot of communication is going on, and I just checked Facebook today, another post popped up with this topic. So let's see the people's opinion here, what they think of this material. Morganite, in my case, I prefer the pinkish variety of morganite. I know there's a lot of orange material as well, and it can be found in Brazil. This is Lavra do Urucum, which is one of the major producers of wonderful mineral specimens with a diameter of 30, 40, 50 centimeters, so huge crystals. And of course, for our US colleagues, we have California. This one here is from the White Queen. You see it is a little bit more orange. And of course, there are famous morganites which are perched on these blue pink matrix, I call them, these blue cap tourmalines from the Himalaya, from the tourmaline queen mine, of course. Pakistan also produces some nice morganites, and also Nigeria. To my knowledge, they're coming from the same mine that the aquamarines come from Abuja Leada, it is called. Yeah, red beryl bixbite. We have a complete talk on this. Unfortunately, I did not get yet a piece of rough that I can cut. So this is just two nice examples of crystals that I have. Not too much onto this. Of course, the coloration here is due to a very high concentration, about 2000 ppm of the manganese. And I remember being a child, this is always has been one of my favorite minerals, and I always wanted to have a red beryl. So if you own a red beryl, you must have achieved everything in mineral collecting, was always my idea. So this is for the collecting regions and the sources for the beryls. For gemologists, there is another topic. The topic is called treatments. Whenever a gem or a mineral can be treated, it is done. This is for sure. The question is always, can a scientist or a gemologist find out if it has been treated or not? So first of all, it is important, if you can improve the color, why not do it if it's allowed? And heating, we know all heating from sapphires and rubies. This is called standard procedure, heating up to almost the melting point of 16, 17, 1800 degrees that they're using. So we can heat bluish green aquamarines, and we can reduce the yellow color component. This is due to two facts. What is generally found is there's the chemistry going on. We have iron 3, which is yellow, and this is reduced in the heat to iron 2, which is bluish. So you can drive the greenish, yellow component of the green to almost colorless or blue at least. However, there's a second process, and I already told you about irradiation and the color centers. So irradiation typically produces color centers by knocking atoms out of the crystal lattice, and this is also a source for yellow color. And if you heat a mineral up, the crystal lattice starts to relax. It starts to vibrate. The higher the temperature, the more it vibrates, and everything that's not in place would fall back into place again. And therefore, the reason for the yellow color is quenched, more or less. And you also reduce the yellow color. So what you can do, if you have a beryl that has green color, which is not due to chromium or vanadium like in the emerald, then you can reduce this yellow color component by heating it up to 450, 500 degrees, so not very high temperature, and you get a pure blue color. What you can not achieve is that the color darkens. So you stay with the color density or depth that you have. You just reduce the yellow, and the blue becomes more pure. So this is done frequently, and as I told you, the heating is very low temperature, 450, 500 degrees, does not produce any change in the inclusions. And in most of the aquamarines we're dealing with, we don't have any inclusions at all. So it's almost impossible to identify. There are a couple of tricks with FTIR spectroscopy and things like this. But the problem is, in nature, you always have a bandwidth of these peaks might occur or might not occur. If you have the raw material, record a spectrum, heat the material, record a spectrum, you see the difference. But you have very often heated pieces that have a spectrum that can also be assigned to an unheated piece. So to be really fair, it is not very likely that you can assign a heated beryl without any further knowledge. So heating is the simplest thing of changing color and improving the color. However, irradiation is a very powerful method, and unfortunately, or whatever you think of it, it is done in a lot of places nowadays. So what you can do is you can irradiate light blue materials, introduce these crystal defects, and you end up with a nice yellow material, like the one you see on the right, which is the beryl from Tajikistan. So the story is not new. This material showed up in 2006 approximately, and people were, I know a couple of people who were traveling to Tajikistan trying to locate the mine, and they did not find it, came back frustrated. And I know somebody who saw crystal specimens who he remembered last year. They were sold as being materials from Shigar, being blue aquamarines. And the year afterwards, they returned the same materials on the same matrix. So you really can identify this pieces, and they were yellow. And suddenly they came from Tajikistan. So to me, the story is pretty easy. I still believe that this material is 100% treated. I just, sorry? I just read a report that said, no, it's impossible, because they used this already treated, or I will call it treated, Tajikistan heliodors, and they irradiated it a second time, and they said, yeah, the color changed, and therefore that's the proof that it has not been treated before, which is not quite fair, because you can irradiate at different energy levels, and you can use different powers. You always will produce a different color. And of course, also the basic chemistry that is behind the beryls at the beginning, the aquamarines, will interfere extremely with the irradiation process, and you can get from light yellow to deep orange materials. Just a question of time and money and investment that you take. Also a process that is done on morganites, the irradiation, which will leave a darker, mostly orange hue in the material. And one process which can also be used to make light blue or medium blue aquamarines, very intense violetish blue, is irradiation. And this material is called, please forgive me if I pronounce this wrongly, it's Portuguese, it's machixe or something like this. So these materials have already been known for a couple of decades. They don't have the iron pattern if you record a UV spectrum, but you will have a broad absorption band going up to the near infrared region. And this material has become famous again 2 years ago, as a couple of people, which I happen to know, have bought a finding of these nice violetish blue materials, and GIA just launched a report. And this is a picture from this report where they said, yes, this is this machixe type of beryl. However, the problem with radiation is always it's extremely hard to differentiate between the natural radiation that has been due to potassium, for example, or any radioactive liquids that had the time of a couple of million years to penetrate into the crystal structure, or if it's just in high intensity that was produced by mankind. So the result is the same in the crystal lattice, and therefore, again, this is extremely hard to differentiate, and I don't think that any major lab will just give you an opinion on this, if it's a natural Machiche or if it's a man-made Machiche type. Of course, there are not only treatment, there are also imitations. Imitations can be synthetic beryl, but synthetic beryl, it can be made in every color. So this is no problem. We chemists are really nice guys, and we know a whole periodic table of elements and can put everything inside these solutions. However, in terms of price, it doesn't make sense for too many species. So it is done with emeralds, of course, and it is done with red beryl. With the blue ones or anything else, at least to my knowledge, is done in the lab, but it's not done in a commercial scale. The easiest way to imitate an aquamarine is glass, because the refractive index is very similar. However, glass is not a crystal, therefore you just need to measure some optic properties in order to find out that this is not the real thing. And in most of the cases, what we have to deal with is synthetic spinel. We have here 3 bowls from the German Bitterfeld company. They were producing this in every color and huge sizes. However, they're also, once you have, you know where to look at, they're easy to identify because they have a higher refractive index of 1.72. This is really completely different league. They have a higher density and they're singly refractive because this is a cubic crystal system. And there's something which I want to end my talk, which is a tool. I never leave my house without it, at least when I go to mineral show. This is my 405 nanometer UV laser.
Testing.
So we use the UV laser and irradiate one of these synthetic spinels. It's either this pinkish purple or a different color. This is greenish. And fluorescence or luminescence, to be correct, is something that you will never see in an aquamarine. So with this, I'm done. I hope I could give you a nice introduction and prepare you to the coming talks. And if there are any questions, I'll be glad to answer them. Thank you. Yes, I just see here in the chats that cesium does not have a color. This is right. It does not have a color, but it's the differentiating element for the Vorovianite. Does anyone have any questions?
I was actually hoping some of you would come up with some brilliant questions, but we will have an open panel questions in. So if you thought about it, and you can send a chat to Jolian with a question, and we'll bring them up at the end. So it looks like, thank you very much. That was a very interesting presentation, Clemens, and I do hope that we'll get some more questions because you did give us a lot of information. So we're going to move on now. It would have been, a normal beginning would have been with Dr. Wise, but it seems that Zoom has sort of messed things up for a lot of people. So I apologize, Dr. Mike, but you were probably misinformed as to the start time.
No problem. Lucky I happened to look at my email about 5 minutes ago.
Yeah, thank God for that. Well, look at Dr. Wise has been a valued member of the Smithsonian Institution, one of the most famous museums in the world, for 33 years. He is part of the museum's Mineral and Gem Acquisition Committee, and by golly, I've seen him buying and negotiating with people at the main shows, so I know it's true. And so he just helps decide on what new minerals are going to add to the collection at Smithsonian, and of course those that'll be deacquisitioned. And that's a very important role because it helps a collection stay alive and vibrant. He also plays a very large role in the outreach and educational work of the geology section of the museum. And quite frankly, I don't believe the next part, but he said he's been a student of pegmatites for 40 years. He doesn't look old enough to have been doing that for 40 years, but apparently he says it's true. And I'm so proud as a Canadian to see that he got his PhD from the pegmatite capital of geology studies in Canada, Winnipeg, the University of Manitoba, Winnipeg. He is very knowledgeable of pegmatites, not just from books, but by golly, I think he's been to almost every major pegmatite in the world and worked on it, seen it, looked at it, collected at it. So, and he did, and in his spare time, apparently he's still doing work at North Carolina's very famous location at Hiddenite. So this is a man of many parts and a great deal of information and knowledge to be shared. And I really look forward to hearing his presentation on the geology of the pegmatites for beryl. Dr. Wise.
Thank you, Ray. Yeah, I've seen a lot of pegmatites, but Peter Lickberg's got me beat by a long shot. He's seen many, many more than I have. Okay, so I'm going to give you a very quick, brief overview of the occurrence of beryls and granitic pegmatites, which is one of the things I've been spending, 40 years looking at them. That includes grad school. So let me share my screen here. And we're good? Does everyone see the screen?
Yeah, we're all good.
Okay. So, pegmatites and beryls. Well, most of us know beryl as one of these really great mineral species that collectors and museums love to have in their collections. But a lot of people probably don't realize that beryl is only one of the species as part of the beryl group, which has 8 members. Beryl being the most prominent. Those of you some of you may be familiar with bazite and pozzoite, specifically pozzoite, which is a fairly recent species. But beryl is the predominant member of the beryl group. It is a beryllium aluminum silicate, Be3Al2Si6018. And I've listed here the sort of general chemical formula for the members of the beryl group. The R site is where we have the elements cesium and sodium that occur in the channel sites, and there's also potential for vacancies in these sites. The X site houses beryllium primarily, in the case of beryl. The Y site holds aluminum and some scandium and iron, and a little bit of magnesium if you're talking about the minerals bazite and indiolite. And in the T site, these are the tetrahedral sites. They are occupied predominantly by silicon and aluminum. So here is, in this slide, we have a representation of part of the beryl crystal structure. You might notice right away that there are these open spaces here, and these are what we refer to as the channels. And I'll talk a little bit about that in a moment. But in terms of associating this diagram with the previous slides, these red tetrahedras form, there are 6 of them, and they form these 6-member rings, which create these channels that go along the C-axis of the beryl structure. In the blue sites, or purplish site, I guess, we have the Y site. This is the octahedral site that houses the aluminum, these scandium, and magnesium. And the beryllium sits in these tetrahedral sites, which is shown here by the green polyhedrons in the structure. All of these polyhedrons are connected by oxygen atoms at their apexes, shown by these red balls here. And then the channel sites are where we have the very large cations like sodium, cesium, and perhaps even some water in some cases. Now, many of us are familiar with the different varieties of beryl, the color varieties. We have aquamarine, is the blue variety, heliodor, which are the yellows, to greenish yellow varieties. The pink variety is known as morganite. Goshenite is considered colorless to white. Of course, we know emerald is the dark green variety, and there's bixbyite, which is the deep red or raspberry red variety. Now, there's a reason for these different colors. In the ideal sense of the word, pure beryl would be colorless. It has no chromophores to give it color. And so Goshenites, like you see in this particular specimen, would not have any known chromophores. The major chromophores for aquamarine is Fe2+, and for Heliodor is Fe3+. And the ratios or the proportions of Fe2+ to Fe3+ gives us different shades of green. And this is not to be confused with the deep green color of emerald, which is formed primarily by chromium and or vanadium. The pink and red varieties of beryl get their colors from manganese. In the case of morganite, we have manganese 2+ in the beryl structure, and in mixed bite is predominantly manganese 3+. Now, most people may think that beryl is a fairly common mineral, but when you look at the geologic conditions necessary to create beryl, it's actually beryl is pretty rare. This diagram shows some ranges of beryllium concentrations in different rock types. And you'll notice that most of the ranges for beryllium concentrations are well below 1 parts per million, up to 10 parts per million. But we're interested in granites and pegmatites specifically for this talk. And you can see that for granites, we have a range of roughly 5 parts per million, and same thing for pegmatites, 5 to over 200 parts per million. And generally speaking, the average S-type granite, which are the types of granites that usually form beryllium-bearing pegmatites, those has an average beryllium concentration of about 6 parts per million. So to get beryl in a pegmatite, it takes roughly 35 parts per million beryllium. Now, if you think about this, that if in all other rocks, crustal rocks and mantle rocks, if the beryllium concentration is so low to begin with, it must take some really special geologic conditions to get that low concentration of beryllium up to a minimum of 35 parts per million so that you can produce beryl in pegmatites. And if you look at beryllium-rich pegmatites, specifically those pegmatites that are lithium-dominated, the average beryllium concentration in those pegmatites can be roughly about 200 parts per million. So what exactly are these pegmatites and what do they look like? So for those of you who don't know what pegmatites are, we think of them as igneous rocks. They're typically light colored with a composition both chemically and mineralogically similar to a granite. That is, they contain essential quartz and feldspar primarily. They can have homogeneous to heterogeneous internal structure, which means some of them may be zoned. And of course, they have very large crystal grain size, extremely variable textures, and some pretty exotic mineralogy that is due in large part to enrichment in a lot of rare elements. So we have these unique textures, which are not really seen in a lot of other igneous rocks. So graphic textures, which is this intergrowth of feldspar and quartz, is very common in many granitic pegmatites. In some, we get what we refer to as comb structures, where elongated or prismatic minerals grow nearly perpendicular to the contact of the pegmatites and the surrounding host rock. And then there are some pegmatites which develop layered textures. But it's really that very extremely large, gigantic crystals that really kind of set pegmatites apart from most other igneous rocks. This is a specimen in the Janet Annenberg Hooker Hall of Geology, Gems, and Mineralogy. In our, at the Smithsonian, this particular specimen is from New Hampshire. It's actually part of a much larger crystal, and it weighs roughly 650 kilograms. It's a nice specimen that kids like to crawl all over and sit on. Now, as I mentioned, some pegmatites can be zoned. On the left, I've shown you an example of a zoned pegmatite, and many of the zoned pegmatites show a gradation from the hosting granite to much coarser grain size as you proceed from the margin in towards the center of the pegmatite. Over on the right is a sort of cartoon version of the sort of model pegmatite, if you will, showing various zones and internal units. Now, beryl can occur in any of these zones, if there's enough beryllium present in the pegmatite. And what we often see is that if there are multiple color varieties found in a zone pegmatite, the color usually varies from the outermost zone of the pegmatite as you proceed towards the middle. So in other words, in the outermost zones, the wall zone, for example, even the border zones, if beryl is present, it tends to be more yellowish color or pale green. And as you proceed from the outermost zones towards the interior of the pegs, even towards pockets, you start seeing this transition in color from yellow beryl to bluish color beryl, and finally into pinks and colorless beryls in the most evolved and most highly fractionated parts of the pegmatite. So as an example, here are three images, three field shots. This particular pegmatite on the left is from the Northwest Territories in Canada. It's showing a cluster of yellow beryl with some pink feldspar in the wall zone of the pegmatite. The central diagram here shows some aquamarine crystals in the core zone, which is made up of primarily gray quartz and sort of a buff colored microcline. This is from the Topsom pegmatite in southwestern Maine. And over here on the right, we have from a pocket zone from the Bennett pegmatite in Maine, a sort of peachy orange morganite crystal. And so this sort of is a really good example of what you could potentially find in different pegmatites showing different chemical evolution. So if we were to look at then exactly what sort of chemical changes we're talking about, we can sort of plot them up on this very general slide showing this general trend of beryl chemistry. For simple pegmatites and pegmatites with very simple zones or the outermost zones, the chemistry of the beryls show very low cesium concentrations, but high sodium to lithium ratios. And as the pegmatite becomes more chemically complex, that is, we're talking about pegmatites now becoming more enriched in tantalum and tin and lithium, these complex pegmatites or the innermost zones, any beryl in those pegmatites typically tend to have much higher cesium contents and much lower sodium lithium ratios than we would expect to find in simple pegmatites or pegmatites in the outermost zones. Now, what did this mean in terms of the color of the beryl? Is what we're seeing is that beryls, again, in simple pegmatites or outer zones are yellow to pale green in color. The intermediate zone beryls are more bluish in color, and the beryls found in complex pegmatites, these lithium pegmatites or the innermost zones and pockets of pegmatites, tend to lean toward morganites and goshenite. Now, not only do we see this variation in cesium concentration, but also this corresponds with the increase in manganese and subsequent decrease in iron. And we see this not only in beryl, but also in other minerals like garnets, columbite, tantalite, and tourmalines. Now, there are some who believe that there's also a change in the morphology of the beryl with fractionation or chemical evolution of the pegmatite. And to some degree, that's true. The early beryls from primitive pegmatites or early zones tend to be more prismatic in shape. And as you get into the more complex forms or complex pegmatites, you start seeing more tabular forms, like some of the morganites from Afghanistan. But this doesn't always hold true to form. As we've now seen with some of these new tabular blue beryls that have recently come out of Afghanistan, if this connection of the tabular habit with the composition were to hold true, I would have expected these blue beryls to be more prismatic in shape, and they're clearly not. So it's not really just a simple fact that the chemistry is controlling the morphology or the crystal habit of the beryl. There's other factors involved, the rate of crystallization, other elements that may affect the crystal growth of the beryl that is responsible for whether or not you get a prismatic habit over a tabular habit. So I want to finish up briefly with the types of pegmatites that we find beryl in, because not all pegmatites are the same, chemically speaking. My former advisor, Peter Cherney, back in 1991, decided or put together this classification scheme. It's a chemical classification scheme primarily, where he identified two major chemical categories. Pegmatites, which he referred to as LCT, which is short for lithium, cesium, tantalum pegmatites, and then this other group called NYF, or niobium, yttrium plus rare earth, and fluorine-rich pegmatites. And then there's a third category, which he called mixed types, which has chemistry and mineralogy that combines both the LCT and NYF characteristics. Now, why do I mention this? Well, because the mineralogy for these two types, LCT and NYF, are vastly different, but they both contain beryl. And the beryls are slightly different in terms of whether you're dealing with an LCT type system or an NYF type system. The LCT type pegmatites are related to what we refer to as S-type granites, which form during the collision of continents primarily. And in that collision, you get thickening of the crust and melting of rocks, which create a magma, which subsequently will crystallize into granites. These specific granites are very luminal rich. We refer to them as paraluminous granites, and they often produce and spawn granitic pegmatites. And in many cases, the pegmatites that are spawned from these granites fan out in this radial pattern, or what we would like to refer to as regional zonation. If you can identify, or if this regional zonation does exist, what we typically see is that pegmatites closest to the parent granite are typically barren. That is, they produce or carry primarily feldspar, quartz, muscovite, and really no rare element minerals like beryls, columbites, and lithium minerals. But as you proceed further and further away from the parental granite, we start to see the development of beryllium mineralization, primarily in the form of beryl, and subsequently the presence of niobium tantalum, phosphate minerals, and finally lithium and cesium mineralizations. Now, if we look specifically or primarily just at the occurrence of beryl, we find that the beryl that occurs in these pegmatites from LCT granite pegmatite systems, in a way, kind of follows what I just spoke about in individual pegmatites. So in other words, beryl from very early crystallizing pegmatites tend to be yellow in color, and as you proceed outward from this zoning pattern to more complex and chemically enriched pegmatites, the beryl color changes from yellow to green through blue to pinks. And so in a way, you could almost use beryl as sort of an indicator of chemical evolution in a granite pegmatite system if you can sort of pinpoint which color of beryl you're dealing with and what type of pegmatite that you're dealing with. Now, if we shift over to the NYF pegmatites, these pegmatites are related to what we refer to as anorogenic granites, which form from a different tectonic setting. And that tectonic setting is really primarily extension or a pull apart of the crust, and you get upwelling of mantle magmas, which then crystallize and form granites. And those magmas have a completely different chemistry than the granites from the S-type systems. The pegmatites that are related here are typically fluorine-rich. They're rich in rare elements, rare earth elements like yttrium and cesium and gadolinium and things like that, and very poor in lithium and boron. So the beryl, to summarize, the beryl and LCT pegmatites, the varieties we typically see are aquamarine, green beryls, morganites, and goshenites. And these are found in pegmatites that are poorly to well zoned. They have moderate to advanced levels of rare element fractionation, and we see enrichment in beryllium, niobium tantalum, phosphorus, lithium, cesium, and boron, elements that create minerals like schorl and elbaite, columbite tantalite group minerals, calcium iron phosphates like tripholite, lithiophyllite, or basite and sarcopside, and a suite of lithium minerals like spodumene, lepidolite, and the cesium mineral pollucite, which is the extreme fractionation of granitic pegmatites related to S-type granites. In the case of the NYF pegmatites, the beryl varieties are not as diverse. Primarily, they're dominated by aquamarine and heliodor, and morganite is extremely rare. I think I may know of only a handful of localities where morganite has been confirmed to be part of an NYF A-type granite pegmatite systems. Like the LCT pegmatites, the pegmatites of NYF category are poorly to poorly zoned. But again, the rare element signature is different. There is this enrichment in beryllium, of course, but it's the rare earth elements that sets them apart from pegmatites of the LCT category. And subsequently, the mineralogy, the accessory mineralogy is different. We see fluorine-rich minerals like topaz and fluorite present, zinwaldite, which is a lithium iron fluorine dominant mica, and gadolinite, which is a beryllium aluminum silicate, monazite, xenotime, which are both RAE phosphate minerals. Oops. So I want to end here with three of my favorite specimens from the collection. They're all examples of aquamarine from different places. The ones on the left and the one in the middle are both from Brazil. The far right is from Monteiro, which is defined as an NYF A-type granite pegmatite system. The middle specimen is what we call the Dom Pedro aquamarine. It is about almost 2 feet high, and it was cut, excuse me, 1.5 feet high, and it was cut from about a 2.5 foot long crystal that was found in Minas Gerais. And then the one on the left, which I think is a really neat little oddball crystal, showing a white cap and sort of sea green base. We like to refer to it as the beer barrel. It has a bit of a head on the top. And the reason that one's one of my particular favorites is because it's an example of how the conditions change as that particular barrel was forming. We think, or I think at least, that the white part of the barrel, which you could arguably call it goshenite, is actually a part of the barrel that's filled with fluid inclusions, as opposed to the bottom half of the barrel, which is clearly colored by the chromophore iron. And I will end my talk there, and we'll be happy to take any questions that anyone might have. Thank you.
Thanks so much. Can you leave that picture up for a minute, Bill, please? Mike, sorry.
The last one?
Yep.
Okay, let me go back.
Because, oh,
No, I'll get there.
sorry. Yeah, because in my introduction, I made mention of the largest known cut aquamarine in the world, and the center one is a picture of it. So I just want people to realize, to coordinate what I was talking about earlier, this is just a small sample of the incredible stuff that's in the Smithsonian. As far as I'm concerned, repository of perhaps the best specimens and the largest and finest specimens in the world. I know the MIM is trying to catch up with you, but I don't think they're ever going to make it.
Well, they have a different focus. I mean, yeah, we have some great things, but remember, our focus is also as much of a scientific collection as it is a collection for public exhibition. So we have a lot of ugly things in the collection as well as a lot of really nice things.
Well, thank you very much for that. Has anybody got any questions? Please be not so shy. Everybody's being very quiet. There's some smart people sitting in this audience, and I know they must have a question for you. In terms of morganite, the one thing I didn't see you mention was the Ocean View mine in California, which has been putting out some nice morganites. I've seen some very nicely cut ones coming out of there.
Yeah, we don't have one of those. We got one of their good kunzite, but not a good morganite from there.
Yeah, they do have some nice kunzites there, that's for sure.
Yeah.
All right. Well, thank you very much. I'm glad we made it. I'm hoping some people will show up now because some people don't believe this is starting until now. And unfortunately for them, they've missed some of the best part of the program, but that having been said, they're still good to come. So not only are we blessed with having a very good introduction to the geology and the geochemistry of the mineral and gem beryl, but also we have the good luck of having some people amongst us here who are going to present that actually have been out there collecting. And I think I've had to invent a new term for the next presenter. I think it's peg maniac because Peter Lichtberg has spent enormous amounts of his personal time and wealth to go and collect it as many of the world's famous and maybe some not so well-known pegmatites in the world to find some of the finest and help find some of the finest gem beryls in the case of what we're talking about today. And I'd like us to give a warm welcome to Peter Lichtberg of Luxembourg. And I don't know whether he's broadcasting from Russia or where he is today, but I'm hoping it's from home. So he's in a closer time zone than he would be if he was in Russia. Anyway, thanks very much, Mike. And if we could have Peter come to open up his screen. Hello, Peter. What happened to Peter?
Do you have to unmute him?
No, he can unmute himself.
Yeah, he's muted.
Peter, you're muted. Don't you just love technology?
Peter, I think you can talk now. You're not muted. Except we can't hear you.
Yep. That voice, by the way, is the world famous Jolion Ralph, who's the our host, Zoom host, and technological whiz kid and programmer extraordinaire who's brought the world gemdat.org and mindat.org. So I'm greatly honored that he's helping this program happen. But at the moment, we need Peter. Peter, you've changed. Peter spent a lot of time trying to downsize his collection of photos so that he can, because he's been to so many places. I don't know of anybody who has been to as many places as he has. I don't even know if he works. Don't say that to his boss, though.
No, we can't hear you, Peter. There's no audio. I think try to change your microphone setting within Zoom.
Unmute. It's unmute.
There we go.
Hey, that's it.
Well, I just muted and unmuted again. I'm sorry. I apologize for that.
We're having all sorts of Zoom problems today, so this is not the first, probably won't be the last.
All right, so I will start sharing my screen. Let's see, and can you see me now?
Yep. I haven't seen, you can't see your screen share yet, though, Peter.
Oh, you don't see that?
No, we see a talking head that's got nice hair.
Okay, so how about now?
Yep, there you go.
Okay, very good.
It's not focused yet, but it's the whole screen.
Okay, good.
There you go. There we go.
Very good. Well, I thank the previous speakers, Dr. Clemens Schwarz and Dr. Mike Weiss, for their introductions, which were excellent. Meanwhile, I took away a few images that I had, so we won't have too much overlapping. So anyway, I will speak about primarily beryl from pegmatites, and obviously we want to see some of the more beautiful, because this is a gem discussions we're having. So it's primarily from gem pegmatites. Now there's some gem quality beryl also in graysons and more hydrothermal deposits. If you think of a granite intrusion, which might Weiss introduced around this granite intrusion. You can have pegmatites within the granite, you can have penetrating up through whatever the surrounding rock is, and at different stages, different heights, you will have different type. If it's reaching closer to the surface, not at very shallow depth, you will, in fact, if it's coming up, you will have a rhyolitic like the red barrels and so on. But below, if it's maybe a depth of 1 kilometer, you can have grayson, and then deeper down. So even in some intrusions, you can see from grayson down to pegmatites where it has been exposed on the surface. So I will talk about a few different regions of the world, but I will start with the creation of the elements. So of course, hydrogen, helium, lithium, beryllium. Beryllium is the fourth element. So of course, from the Big Bang, it was one of the first elements that was created. The first mineral species was probably diamond, pure carbon. And I will not speak much about astrophysics, which I'm not expert at all, but what is interesting is that the Earth is in fact unique. Of course, we have the mantle, we have the core, but because we have the plate tectonics and we have an atmosphere and we have water, we are creating a lot of different mineral species. Now, here is just an overview. Up to iron, nickel, you can create, but any larger, you need really a supernova explosion. So here I took away some more detail, which we've already seen, but we have been subducted 2020. We hope for a better 2021. This one, we have 92 elements on the planet and 5,600 minerals, while other planets maybe have 50 to 120 mineral species. People always ask me, don't you want to go to Mars and look for minerals? Well, in fact, Earth is the perfect place. When we look at we have the plate tectonics here and the oxygen and water, as I said. And when we look at the first minerals of beryllium, it is beryl. The oldest known beryllium mineral is 2.95 billion years old. And to come to there, here we have some, magmas, igneous rock coming up to the surface is typical here from volcanoes in Chile. Composition can, vary from felsic basaltic. And here is typical granite. This is from the west coast of Sweden. Now you see pegmatitic veins to the left and to the right. And to the right, you see a larger where grass is growing in a pocket. Now the pocket can be in the center. It can be offset towards the side. And here is a granitic pegmatite in the granite to the right, where it doesn't contain pocket, but it's crystallized within its mother granite, parental granite, or it can penetrate further up. Here is one which is sewn in a number of layers. There's not much of rare minerals in this one, but as Mike Weiss was showing, it depends on, it could crystallize with rare earth elements, lithium, beryllium, and rare elements within the granite in some pegmatites, which I will come to, or penetrate up. Here is from Iveland Evje area of Norway. You can see there is amazonite up to the right of the amazonite is topaz, the white here. There are barrels down here. There's spessartine garnets. Here is a big spray of elenite, ortite that is. There's clevelandite here, and this is a good example. There's a lot of rare earth elements in this pegmatite, and like Mike said about Cherney's classification, lithium was discovered in Sweden at Ute Island, so more than 200 years ago. So we always call them lithium pegmatites. Then if you want to see the fractionation trend of lithium, of course it is cesium and tantalum. And rare earth element pegmatites were started to be mined. Rare earth elements were first described from Ytterby pegmatites north of Stockholm. So in fact, the two types of pegmatite were described more than 200 years ago from Sweden. And the first mining in Ytterby was 1756. That's been documented. Here is Högsbo pegmatite, big pegmatite, 10 to 12 meter wide. This is near the core zone, a quite large barrel, which is nice. My little brother there, he came along because I found this very big barrel and I wanted to show him. Now, when it comes to ages of pegmatites, you can see to the left, like I mentioned before, Gravelot emeralds from South Africa, the first known barrels on the planet compared to 4.6 billion years old. They're 2.95 billion years old. Then I have marked some. These are the main pegmatite time period. You can see to the left number of pegmatite fields from each period. Volhynia, Ukraine, 1.7 billion. Karelia, Finland is almost the same, 1.63 billion. Then I marked Scandinavia, Brazil, Urals, California, the Himalayas, and I marked up, Pakistan and so on. So the young pegmatites in Pakistan, which are 8 to 12, the older ones into Tajikistan, 23 million years old, similar in Burma and Vietnam. So which means Vietnam, you can see very, very beautiful blue aquamarines. In Pakistan, like Clemens mentioned, if you have iron 2+ and very, very, low percent, well, it's per mil of iron, then you will have very pale aquamarine. So what do you do with them? If you irradiate them, you can get a much better yellow color than a blue. And in fact, in a pegmatite, which is 8 million years old in Shigar, you will not have had very much radiation from potassium 40 or even thorium or uranium to create any yellow beryl. So the first one were shown from Pakistan. There was Shigar specimen from Shuma Bakur from a Grayson deposit. They were shown and they were irradiated. They said they were natural. And I spoke with the guy. That was Tucson 1993. And after half an hour, he agreed, yes, we have irradiated them. And I brought 2 examples. I measured, you couldn't see the induced radiation because they had probably used linear accelerator. I measured all night underground in an environment where you don't have any radiation from cosmos or the Earth. So here is an example of this oldest beryl from Gravelot. And this one was pictured in Sincanca. It's interesting because it's the nicest piece I've seen, which is very well documented. It's Sincanca's sketch and painting of the specimen. Now I have just marked some of the pegmatite regions. We will start in Ukraine and Finland. So Ukraine and Finland, in fact, we started Finland and Ukraine, which is like Mike Weiss mentioned, it was A-type granite, a stretching of the earth crust. So in Finland, we can see in the Viborg massif, it's about 20 kilometers thick in the center. And to the sides of it is 55, 60 kilometers thick, the earth crust. So you had a stretching. If you take a pancake and pull aside, you'll have thinner in the middle. And that's what happened. And those Rapakivi-type granites that those camber-type pegmatites occur in, they are all very old. Now, what we will see on the surface depends on the erosion level. So in Finland, we have lower erosion level than in Ukraine, which means that the pegmatites that gather near the apex of the intrusion, they will be the ones visible. In Ukraine, we have a deeper erosion, so you will have exposure of the ones which is around, circling around on the outskirts of this intrusion, right near the edge to the surrounding rocks. Then we will go to the Ural Mountains, which is the largest marked here. And then we'll go to some of the newer pegmatites in Afghanistan, pegmatites very briefly. I can't discuss all parts of the world because then it would be about 5 times as long. Now here we see to the left, huge frozen beryls from Portugal, and to the right from Pakistan, a huge pocket, which I will mention later on. So starting in Karelia, Volodar's Ural Mountains, I will not speak about Altai, but in the oldest, they found some huge aquamarine crystals in Altai. And in fact, in the literature, they mentioned that there were some huge ones that were in fact gemmy. And we will go to Adon Chilon and Shelovagora. It's interesting because it's the same granitic intrusion, but Adon Chilon are pegmatites, it's eroded, and Shelovagora is the same granitic intrusion, but it's higher up and it's a Grayson deposit. Karelia beryl mine, it was in fact discovered. It's called Lumäki in the first literature. It is near Lumäki, but the mining company is Karelia Beryl, and the mine, official mining claim is Karelia Mine. So Karelia Beryl Mine is in fact the composition of the two, which gives more information. You see to the left, this is a photo from 1980s with a big beryl frozen in the pegmatite. There are many different types of pockets in this. I haven't described them all. I should do a serious article on this. And where you see the excavator is digging, that is a very, very late stage hydrothermal pocket where the best crystals occurred. So very late stage. And I have documented all this. I have photographed, I have it all. There was one PhD thesis written now, but he has not seen this. He just analyzed, in fact, the geochemistry of them, where you can also draw this conclusion. But I had already published years and years ago about this. So here you to the left, you see Heliodor in situ, frozen. In this pocket, the hydrothermal, there are no quartz crystals and not very good feldspar crystals, very, very late stage. And the crystal to the right, 1.2 kilo, absolutely fantastic. So my friends and I, they mined most of them, and I went up when they started mining the best part of the pocket, and that was in May 2004. And those crystals came out. I have many, many pictures from this pocket and from the best crystals. We go to Ukraine, and here you can see up to the right, the Korostin Pluton, a geological map. So if you have granite intrusion 40, 50 kilometers big, you will have segregation of rare earth elements, with some pegmatites, depending on what was the composition originally, of course, and the fractionation. You might just have a few, or you may have many. Now on the west edge, in fact, Korostin is not very well discovered, but all around the Pluton, there is probably chamber pegmatites. They were only mined on the west side, a little bit south, and the east side were drilled and test mined. And they mined 1,900 pegmatites here to the left, along the edge, 22-kilometer long belt. I have visited those mines systematically since 1995, which means that I will fly down for a weekend if there's something to see. Some years I fly every month down. So sometimes I go down for a week. I've been there, but this is my holiday. And they started to mine piezo quartz. The first find was in fact in 1850s already. In 1931, the Soviet army started mining for piezo quartz. And this is what the chamber. So these are cogenetic with the granite. They are within the granite which they form. It's like a huge bubble. Depending on the composition, they will have different shape. So here above us, you can see the big quartz core, which is high up in this pegmatite. The quartz crystallized higher up, and you had a secondary leaching of the pocket floor with recrystallization of the quartz up, which means they formed quartz crystals up to 10 tons. And here is a big topaz. We found in 2013, we found a 325 kilo bicolor topaz. Now I'll speak more about beryls. Photo to the left is from the largest chamber of beryl. In 1982, there was 1 ton taking out just as, to give to museums. And in 1992, when Soviet Union had fell apart, they found out that in fact they could get some money. And they started to mine, and then mined over 1 ton. They mined 900 kilo within 5 days, 5 miners in this pocket. And they're world famous. Now here is quartz crystals left in a pocket in 1973. So you can imagine how much and big quartz crystals they were mining when they even just left this in the pocket. And the same pocket, there was just the resting. I just gathered a few barrels on the floor. This was within 10 minutes I gathered those. They were small, well, the bigger in the middle is like the thumb, but still they left them. They took out in 1973 260 kilogram of barrels and gave to institutions. And you see them sometimes at shows from very old collections. In 2007, I documented the first in situ barrels. Nobody had ever documented photographs, and we could understand that the barrels had crystallized on albite at the bottom of the pocket, but this had been leached out. So in this pocket, I found the first heliodors where you still had the albite under, but I was really looking, I was digging there many, many times, and it was so poor oxygen that your face was swollen and red, and many of the miners had heart problems 2007, 2008 in this tunnel. And here is the upper one you just saw in my hand to the left. Here is a big topaz. Now we will not look too much more in Volodas, but it's such a fine deposit with 2% of the 1900 pegmatites contain beryl. So you understand from all this pegmatite 2%, which is like Mike Weiss spoke about the fractionation of all these pegmatites that are highly fractionated already. 2% contain beryl at all, and just a few of them in very high quality. And each pocket is unique. Each pocket has different shape, has a bit different mineralogy, and completely different etching of beryl. So here is the chief geologist and I. We're probably the only ones together with his son who can distinguish from exactly which pocket the crystal came from. And here is a suite of cut stones, all from Valdars, all natural colors. You see some beryls, yellow, yellowish green, aquamarine, and topaz of various colors. Now, these pegmatites are 1.7 billion years old, which means they had a lot of radiation. The radiation causes this peachy color in the topaz and yellowish color in the Heliodor. I didn't say it, but in Finland, in this fantastic pocket with the green crystals, in the outer zone within the biotite lining, there were yellow Heliodors. So depending on the radiation they got, and of course, during 1.6 billion years old, it's a lot of radiation. Now we go to the Urals. Pegmatites about 300 million years old. They were very famous. After Russian Revolution, we didn't know much what was happening there. So I went there in 1992. It took many, many years to get permission. And here I made a sketch. All the yellow veins are pegmatite veins. They strike north-northwest. And to the right, the purple are amethyst veins. The amethyst veins are within the granite intrusion. So the pegmatites are just outside the granite, but the granite is dipping down under. So to the right, the pink is the granite, and you see some to the left. And here the pegmatite veins are red. Here is Kasionitsa mine. I was there 1992, January 93, and I went there several times to follow the mining. This was the last gem pegmatite in Mursinka, Alabaska, and the Russians, they had never done any underground photography of pockets and so on. So those are very rare images. I have many, many, but I just show you a couple. And here is a cross section of the Kasionitsa pegmatite vein. The yellow are Heliodor beryl containing pockets, and green is beryl and topaz, and blue is just topaz. So there were 352 pockets in this pegmatite, and just a few had beryl or topaz. And you see the Heliodor crystals to the right here, the upper two to the right, they came from the pocket 261, which is right here, just under this crystal. And this one here came from pocket 99. So I helped the mine to document every crystal, where it came from and so on. I photographed everything that I could. And here are some of the crystals on my first visit. Here is one piece that I documented, and later this source information from one dealer to another to a collector, it disappears, which is sad because it is known exactly where it came from. And this is, I think it's very important with all specimens, not just, and sometimes the specimens change even country, which is not very serious. Here is a range of colors of beryls from Russia. There's one in the middle, which is from Ukraine. All the others are from different deposits in Russia. Here are, when I've been to the Urals the first time, I made this photograph of beautiful Heliodors from the Golodnaya mine in Alabashka. And here my wife has designed a ring. It was cut by Michael Gray, but very, very beautiful color. Here's my wife's design again. This is a Museum of Natural History exhibit going on right now till June the 6th, a big gem exhibit in Luxembourg. And the beautiful, we spoke about beautiful aquamarine, or Dr. Schwarzinger spoke about the most beautiful aquamarine. That's a lovely example to the left there, 51 carat stone. And here are two pieces, and you see I've noted for you just now who found it, which date, and they're both Heliodors to the right from the pocket, which I just showed you, 261. Now to the left here is from another famous find in Adu during 2 weeks, just end of December 1899, first week of January 1900, at the depth of 22 meters in the Semenitchinskaya Kopy. They found this fantastic pocket with several hundred kilos of green aquamarines, and this crystal was bought in 1903 in Mursinka. The crystal to the right came in the late 1700s to Germany. So some things, oh, it doesn't matter. Some in the gem business think, oh, it doesn't matter from which locality. Well, that's very important because they have a problem. Why should you pay more for a specimen or a gem from one locality? Well, why should you pay more for a painter by Rembrandt? If you have a painting, it's just a beautiful oil painting. It's just a beautiful beryl. So if you know that it's Rembrandt, if you know who is, if it's a portrait, who is on the portrait, of course it has much more scientific interest. Here are another couple to the left from Svetloya pegmatites, not so well known as a granite and kaolin quarry, south of Yekaterinburg. So one aquamarine up and one Heliodor. And to the right is from Ilyutin Chukotka Island, there's in fact a scheelite and cassiterite deposits. There's more Grayson. Here we have from Ural emerald mines. So in the Urals, of course, Urals is north-south stretching. We have pegmatite, granitic intrusion with pegmatites in the middle, you could say. It's a little bit on the east side of the apex of the mountains. Now in the contact to the east, you have a lot of chromium carrying rocks. So when the granitic pegmatites penetrated through those rocks, they got contaminated with chromium and vanadium. So there you have big, well, probably the largest emerald deposit in the world. In fact, it extends very, very far, but the largest one is about 10 kilometers north to south. And here is from the mine, the Mariinsky mine, my first visit in 1992. And in fact, when I was in the Urals, nobody had been in the gem pegmatite since 1916, before Russian Revolution. Here is Federico Balocher, a huge emerald from Mariinsky mine. He had a few years ago at the San Maria Min show. And here is a lovely piece that a German collector had exchanged with the museum in 1980. And he cleaned it, I cleaned it. And from the back side came this cut stone, which you see there, which I gave to my wife on her 30th birthday. So that's a fantastic Russian emerald, but it's very rarely we see them. And this was, of course, from a very old piece. And the last couple of decades, they have been mining again, but in principle, the mines were closed when I was there in the 90s. They were not running very much. Now I come to this, I told you Adon Chilon and Shellavagora. I marked Adon Chilon, circled it in the middle, and that is, it has eroded. It is higher than Shellavagora, but it's the same granite intrusion that dips down, and up to the right, you have Shellavagora Grayson. And this is Adon Chilon. You see the topography of the mountains, beautiful pegmatites. They're almost chimney style. They are very, very steep and round. So they're not, here we see Adon Chilon. And here's Shellavagora. Those are thin veins, up to some meters wide veins, filled with both beryl, quartz, and topaz. But each vein is different here as well. They also have different colors. Here in Shellavagora, it goes from anything to blue to green to strong helidor. Blue and green are the most common. And here are examples. To the right is Spinello twin fluorite. And here is a big Shellavagora aquamarine. Most pieces from the last few years were sold to China. The Chinese are very eager to buy stones for cutting and specimens. So we will now go to the youngest pegmatites on the planet, some of the youngest in very briefly Hindu Kush in Afghanistan, and then on to Karakoram. So to the left, you see the Afghan pegmatites, to the right, the Pakistani. What is special is that it's very, very high altitude, up to 5,000 in Afghanistan and same in Pakistan, although the mountains are over 8,000 meters around the gem pegmatites. Here is from Paprok, Afghanistan. In the 90s, I sent cameras with, because people didn't have telephones with cameras those days. So I bought several cameras, even video cameras, and sent with the miners and via the dealers in Peshawar, just asked them to take pictures for me so I can see. And they said the whole mountain is full of pegmatites. So this is from Paprok to the left. I wrote in the Mineralogical Record one article on gem pegmatites of Afghanistan. It's just a summary. But of course, they are most famous for tourmaline and kunzite, but there's some beautiful morganites. Here's just a map. And here's Paprok, the Loimaden, almost 5,000, 4,700 meters altitude. And here's a German Mineralienwelt I published quite a few years ago about Paprok. And here to the left, you see a typical aquamarine morganite. Several of the mines have these aquamarine morganite combinations there, and most famous for tourmaline and so on. Here is the big Maui pegmatite. Mike Weiss spoke about zonation of the colors within pegmatites. Here down below at the bottom of this pegmatite, you have huge frozen aquamarines, and higher up within the same pegmatite vein, not only in pegmatite system, you do have the morganite, late stage, higher fractionation pockets. And here is one from the Maui, very beautiful morganite. Now we go to Pakistan, also very young, even younger pegmatites. So we have age-dated Brendan Lors, who worked for GIA, now works at GEMA in London. He did his master thesis there, and he age-dated several, 8 million, 12 million years old. And for sure, pegmatites are still forming. So of course they form a bit down, but pegmatites are still forming here, which is very interesting. So if we will look in 100 million years time, we will age date and see maybe there were 2 generations, 3, but in reality, maybe there are 100 generations of pegmatites really in reality. So India collided with the Asian plate, and the Nanga Parbat Haramosh is really the top of this plate that was uplifted about 8 kilometers. So very high altitude mountains, 7,500 to 8,600 meters. And here's Shuma Bakur, very cold. Here's the mining camp. And here you can see, this is not pegmatite. These are thin hydrothermal, I should say. I've written pneumatolytic. In fact, there is a granite intrusion, which I understand is about 300 meters below. But still, there used to be aquamarines in one huge quartz pod also. So you have, numerous occurrences, at least 2 different types here. But most are very, very thin veins that open up, lined with muscovite. In Xiaobaoding in China, you have beryl together with scheelite and cassiterite and so on. Very similar to that, I would say. I've said this since 1985 when I saw the first pieces with matrix. There was not any pegmatite really, although we could call it pegmatitic because of the big crystals, but not in the sense of granitic pegmatites. And here is a typical find 1 year, many, many pockets with some pink fluorites they find also, and some nice quartzes also. And this is a very well-colored aquamarine from here. Now we're going to go to Haramosh, which Clemens showed a beautiful aquamarine from, and then we go over to Shigar Braldo. So this is Haramosh Peak. When I went to Pakistan the first time, I had been looking, as soon as Google Earth came, I looked at all mountains of Pakistan, Afghanistan, and I looked, and people were saying, all the dealers said everything was from Shigar and Braldo. I could look at the specimen, see they must come from very high altitude near the surface. I think they were formed at much lower depths, looking even just at the albites, the structure of the albite. And it's, I found some pegmatites on Google Earth and I went there. So I wanted to go to the most difficult deposit first and see what time. I think I had 6 weeks the first trip I went, and I wanted to go to the most difficult places first. So if you look to the very right, there's some pinnacles up here. There are 4,800, 5,000, and up to the left 5,500 meters. And I climbed up there from the other side. And this is what it looks like. You see this vertical cliff. Oh, these are among the lower mines. And you see the peaks here, 7,400 meters. I slept up there on the cliff. I've never met this guy. He's a miner there. I met him on the way up the mountain. And here I am with his brother in an aquamarine pocket. And this is the quality. Clemens knows his crystal, which is fantastic. The crystal you see to the right, it's very, very thin and still has an incredible color. So there are a couple of mines in Shigarval that has fantastic color, but it's very rare. Usually they're much lighter. And the very best piece that came from Haramosh, only those pegmatites have very, very few pockets. And when they hit the pocket, about every 10 years, it's a decent pocket. There may be 1 or 2 specimens, while in Shigar, you can have hundreds of crystals in a pocket. And there are also emeralds. There are several places there on Kaltara Glacier. So emeralds in pegmatites here. Sometimes there are, in fact, there are emeralds in one of the pegmatites here in pockets where you have bicolor. You have goshenite and then half is emerald, which is very cool. Here is an example from Shengus, a morganite to the left that I photographed when it came out of the mine. And to the right, it shows up in Tucson and it's from Afghanistan, which is a shame because it's known, it has been trimmed as you see and tilted, but it's the same specimen. Now I come to, when I was there the first time, I suggested to miners, you see this cliff with plenty of holes. I told them, why are you going? They went 2,000 meters higher up, 4,500 meters. So they could only mine 2-3 months per year. And I looked at this cliff and I could see dozens of pegmatites, and you could see from the erosion inundations. And there were 3 small tunnels at the base of the cliff. I said, why don't you mine here? I told the landowner, if I were you, I would mine here underground year round. And every 10 years, you will find a nice pocket. And there's many, many small pockets you find meanwhile might pay for the mining. So this is what the cliff looked like before on my first visit. And there were 3 tunnels, here are 2 of them. And this is what it looks like now. And this pocket was found in 2019, so just about 2 years ago, and incredible. And this is the finest large aquamarine specimen that mankind has seen, and the most beautiful aquamarine pocket. And here is a specimen, 34 big aquamarine crystals. Here is another piece from a nearby pocket found a few years earlier. And this is what Shigar and Braldo Valley are known for, fantastic matrices. We never see anything like this from Brazil. Mostly Brazilian pegmatites are heavily eroded, became kaolinized, the feldspars, you find a loose crystal in the clay. And that's the last place we're going to visit, the pegmatites of Brazil. You have a lot of rare earth element pegmatites, there's some lithium. In fact, there are different regions, and I will just show you a couple of the aquamarines from here. You have the Inselbergs, the granite intrusions sticking up like this, and around them you have pegmatites. And usually they start digging in the clay and they make a tunnel 2-3 years after maybe half a year. They come in where they encounter the granite. They hammer their way through 50, 100, 200 meters to the granite until they find a pegmatite. It seems very simple, primitive to us, but labor is cheap, mining is still costly. But if they here is one beautiful pocket that hit with some really, really fine aquamarine. And the mine owner's father is here to the right, many years ago with some incredibly large crystals. The left crystal was found in 1910 with the now recently deceased Professor Herman Bank of Ida Robson. His father was living in Arasway 1909 to 1911. And he found this in 1910. The sad thing was that all the collectors who had this one, I saw this on a photo in a book when I was a small child. And the collectors who had it, very wealthy American collectors, they did not find out the real history or keep the history. So I bought it many years ago and I brought it to Professor Bank, and he knew, of course, exactly. So I always have to thank, because as you all know, both Mike and Dr. Schwarzinger, we have to thank our families for letting us be away. I use my holidays to go. So sometimes I bring my family and of course all our collecting friends. Here's the exhibit in Luxembourg going on now. And I hope to see you again in some other conference. I'm sorry I missed the tourmaline one. Any questions, I'll be happy to answer.
I think we have the shyest audience on the planet.
Yes.
It might be a testimonial to the level and quantity of information you shared, though, Peter.
Well, it was a brief overview, but I hope I gave an introduction at least to some of the areas. I did not speak so much about the lithium pegmatites because I thought Mike would speak. Well, he showed from Maine, this beautiful Rose of Maine, which is fantastic. And of course, the California pegmatites, we have some absolutely lovely morganites. And in Correjo Rocum, which we saw examples of, which is, there was a tremendous pocket in the old days with beautiful large morganites with tourmaline on and so on.
Well, that was a very truncated, I'm sure, because you had to do a lot of condensing, but a truncated version of some of the things that you've seen over the last number of decades as a collector. And I still think the term pegmaniac does apply to you, Peter. I don't know anybody else who's invested as much time and holidays and money into learning about pegmatites and peg gems. So thank you very much for sharing that knowledge and some of those images with us. I know it took you a bit of time to do that. Our final presenter, if there aren't any questions at this moment for Peter, is a young gentleman. Just let me pull up my notes here so I don't get it wrong. I just was recently made aware of this gentleman's existence, which is a sad loss on my part because I would like to have known him earlier. I am a keen collector of gems, and this gentleman's name is Seth Rosendahl. He was born in Iowa, and he still lives there, I think on a farm, but I'm not sure. And for more than 8 years, he has totally immersed himself in one single entity, Red Barrel. He sold his business and basically committed as much of himself as he could to learning about collecting, amassing, and writing about. Actually, I think he's written 3 books so far on red barrels. and I know he's going to share with you some of his passion. So I'm going to call your attention to Seth Rosendahl and ask him to start presenting, if he would, and sharing with us what he knows about probably the rarest of all the gem barrels, the red barrel. Seth, are you there?
Yeah, I'm here. Thanks. Thanks for that introduction. And I just wanted to thank you, Ray, for having me here today. I guess in 2013, as he said, I sold my business and all my assets to invest in this gemstone. I stumbled across an online auction for a red emerald crystal. And like most people, I thought, but there's no such thing. So that's basically what launched my investigation into this. And I had to ask myself, well, what is an emerald? In antiquity, every green stone was considered to be an emerald. But today we know there are a lot of other things that a gemstone must be to qualify for that term. And as I became aware of more of what all of those characteristics were, the more my mind became satisfied that all those things are what a red barrel actually is, by any name. I know that some are vehemently opposed to the term red emerald, and I'm not trying to convert anybody, but it's important to understand why other people think that. And part of my mission is I try to broker some kind of peace accord between the mineralogists and everybody who might use that term. Because I think the big disconnect in the larger industry is that I consider the mineral red beryl, but the gemstone as a red emerald. So in 2018, the AGTA, I worked with them and some other people, and they issued a letter to the Federal Trade Commission that stated they will defend their members when they use the term red emerald in sales. So it's important to realize that that name is not just going to go away. One of the strongest supporters, in my opinion, for this term is Dr. James Shigley, who many people know was the head of research for the Gemological Institute of America for more than 30 years. Except for the very first article they published, he's written everything that they've ever put out on the subject. And Dr. Shigley graciously allowed me to share his position on this issue. And this is a direct quote from him. He said, "Red emerald better communicates what the material is to the public, and the term does not misrepresent the identity of the material." So today, I'm going to cover just some of the reasons that he believes that, and why I personally do as well. One of the reasons I prefer to use that term is because I feel my main job is to educate the public and increase awareness of this gem mineral, which most people have never heard of. And as you'll see today, I can't very well explain what a red beryl is and what its characteristics are without also explaining the aspects of what a green emerald is. So without any further ado, let's just get right into it. Can you all see that?
Yep.
Perfect. Okay, so today we'll do a virtual tour of the Ruby Violet claims in the Wawa Mountains of Utah, which is the world's only locality where gem quality red beryl can be mined. So far, that's the only one we've discovered. And we'll cover the standard red beryl mineral forms, along with the typical modifications you will see to these crystals. I was able to visit the mine site on 2 occasions, and I've spent about a week mining myself. And here's a couple pictures. The first time I caught this nice little red lens flare that gave me a little red rainbow. And the second time there was a storm where we got an actual rainbow. So it's a beautiful place. It's really one of the wonderful spots on Earth, in my opinion. And there's nowhere that I'd really rather be spending time. Here's a shot of the upper mine. There's an upper pit, a middle pit, and a lower pit. And one of the old miners called this the cathedral. And when you stand there, you will see on three sides these very tall cliff faces with just the brightest snow white rhyolite that you can imagine. It's actually almost blinding. And hopefully you can see here on this picture, all of this rock is very heavily fractured with fissures and deep cuts in the stone. The reason for that is when this rhyolite was cooling, it well, there's a geologic process that used to be called pneumatolytic. If you're familiar with the pneumatic drill or pneumatic lines, then you know that it's air under pressure. So as this was cooling and releasing gases, created these little fractures in the rock where the crystals form. I just, you know, you're always learning, and just today I found out that pneumatolytic processes is an obsolete term, and now they are considered hydrothermal. Even when I first started studying it, the processes are the same, the exact same as the ones that occur in the more famous Colombian emeralds, but they occur at different temperature points. Because of the heavy fracturization and previous mining operations that occurred on site, if you ever visit there, you will notice that there are lots of rocks that have fallen off the cliff face or have been broken off the cliff face. And you can actually find, rarely, crystals that are just laying on the ground that have been exposed just through natural weathering. But more often you'll have to dig if you want to find these yourself. And I have, every time I visited, I've gotten plenty of blisters trying to find these. And here my dad's holding up this specimen where you can see the actual fracture line, and where that breaks apart, this little hexagon has grown right in that fracture. One of the things a lot of people may not realize is that although much of the crystallization begins in those fractures, when the crystal forms, it doesn't just have to stay in that vapor cavity. It can displace the actual rhyolite itself. But where it occurs in the vapor phase is where your highest crystal, you know, highest quality crystal is. So you'll see a lot of crystals like this, where you'll have rhyolite, heavy rhyolite inclusions, and then you'll also see where it was within the fracture, you have a higher quality of crystal. Here is an outline of the mineral modifications we'll cover today. And many of these photos were taken from that self-published work that Ray mentioned, which is Red Emerald, the Pink Portfolio. And if you go to my website, theredemerald.com/library, you can download that book and the other publications that we've put out for free. So, because we're going to cover this very quickly today. So we have recurring alterations to the standard prismatic beryl mineral form, which is a prismatic beryl has 2 hexagonal termination ends, 6 rectangular crystal faces. And here we also have from Tulane University a geometric sketch of a dihexagonal dipyramidal prism. And also a sketch from the mineralogical record of an emerald that has alterations to its termination end with beveled points and beveled edges between the termination and the crystal face. And these occur because both the green and the red are crystallizing under very heavy, under very strong pressures, air pressures. And sometimes those edges don't quite pop out, and they get pushed back in. But these are not random. These occur along very precise planes that are at very specific angles. The first alteration that we're going to look at is the pyramidal points, which occur where the edges of crystal faces and the terminations meet. You see this quite often on green emerald crystals, sometimes on aquamarines as well. And here are just some examples of that in the red. Now, when an edge gets pushed in more than just on a point, you will often see these beveled edges that look like the edge of a countertop. Here's a picture of this El Perfecto, a fine specimen from Cosquez. And here is a picture of the Galacha emerald that is housed at the Smithsonian. Both of which have beveled edges. And here are some reds that kind of mirror those same structures. Rarely you will see that same beveling occur on multiple edges of a crystal. And here are some shots of that occurring. Now, when an edge gets pushed in more than just a bevel, it will be inverted. It'll be inverted at precisely a 90-degree angle. And this often occurs like right next to the edge, and it gives the appearance of a stair step right next to the termination. When you get an inverted edge along two crystal faces, the crystal is often grooved, and when it goes all the way across, I call it a trench modification, and that will give you an appearance from the termination end of almost like a heart-looking shape, and you can see that here in the red and the green. When the crystal continues to grow even after like a stair step forms, or when you get a dislocation that causes facial separation, the crystal can continue to grow, and that separate stair step can thicken and grow on its own. And if this is allowed to continue to grow, you will see like multiple prisms intersecting. Here is a shot of the Patricia Emerald, which is all housed at the American Museum of Natural History, and a couple red barrels that show the same type of habit. When these barrels form, they stack molecules, which as we all know are hexagonal shaped. There's a single beryllium atom with 6 oxygen atoms that form in perfect hexagons. And when these grow, they grow outward, and you can actually see the growth just like you see the rings of a tree. And from the very first article that the GIA wrote on this, they've covered this particular phenomenon. The hexagons bond together in hexagonal plates, and these smaller plates combine to form larger and larger hexagonal plates, creating the crystals that we know. Here's a good shot of multiple hexagons on a termination end. When these grow at different rates, they stack at different elevation levels. This is the only picture I have from the Thomas Range, where we often see these rosettes with multiple hexagons. And here's a green example of where there's multiple tiers of these hexagonal wafers. And on this one from the Thomas Range, you can actually see, the lines where the layers of gem crystal stack on top of one another. Here's a sketch from the mineralogical record. that shows the layered emerald growth in parallel. And when these different prisms grow at different rates, you see, again, different elevations of these hexagons on a termination end. And here's an example of that in the red and another example in the green. When these hexagonals grow at different rates at different angles, you'll often see when they're competing, they will grow multiple prisms that intersect with one another. Here is a intersecting prism from Hiddenite, North Carolina, and one with a similar habit from the Wawa Mountains. A lot of times that disrupts the further growth, and you get multiple crystals that propagate and start to form, which you see in this at the bottom of this specimen and this green. When the crystals grow from a single nucleation point, but there is more than one, they often spread from at very precise angles. And here on these two examples on the right, you'll see that they actually have facial modifications that mirror the dihexagonal dipyramidal structure, where the face will get split. And sometimes, very rarely, you'll find 12-sided crystals. And here on the red, you see a half face, and on this screen, you see where the face has actually been split. When they're allowed to grow, multiple clusters will grow at multiple angles, and they create some really phenomenal specimens where you just see many, many prisms all growing together. This is the holy grail of specimen collecting, when you can get a almost perfect hexagonal prism with very little damage and very high gem quality with very few inclusions inside. This usually occurs, again, when it's completely uninhibited in a vapor phase environment. And still, as you can see on this green and the red, you will still have inclusions in both crystals, which is why the GIA categorizes both of these minerals as type 3 gemstones, which almost always have inclusions. But they're phenomenal when you can actually find one that looks like this. And less than 10% of all crystals that have been mined actually attain this state. But when they do, you can create some beautiful gem quality faceted stones. And if you can gather enough of these in quantity, you can make some beautiful world-class jewelry pieces. That's pretty much all I have. I didn't have a lot of time for this presentation, but again, most of the preceding photos were taken from the Pink portfolio, which you can download for free, along with the other books that Ray mentioned. The Black Album shows the standard red beryl prismatic forms, and I have added enough photos in there, which is more than all the other red beryl photos that had ever been published. And then the White Prince is the third book, which shows a lot of the jewelry pieces that we have been able to create so far. I will put a copy of these slides on the website under theredemerald.com/presentation. And any of you who want to contact me personally, you can either add me on Instagram at Red Emerald Sales, or you can send any information you want to SethRosendahl@gmail.com, or visit theredemerald.com, where we add new information almost every day. So thanks for your time, and I hope it was at the very least informative.
Well, that actually is a pretty good definition of your brief and very concentrated presentation, Seth. Thank you. And that's interesting because you see there are a couple of gems in the world that fall in the same category as Bixbyte, Bonitowite being another one location in the world where it can be found. So the availability and to the general public or to the jewelers of the world is quite limited. And so you've actually accomplished something quite unique here, Seth, in your ability to concentrate the amount of material that you've managed to get so far and put together the kind of information you have. Now, I'm sure there's got to be a couple of questions out there about red barrels. Please help me out here, Mike.
Well, there is one thing. There is one thing I would like to mention. The one name that has been depreciated in this mineral variety was SIBJO, the World Jewelry Confederation, actually depreciated the name Bixbyte for its confusion with Bixbyite, which happens all the time because the only places where Bixbyite is found is also the only place where Bixbyte is found. So I personally, I don't care what name people use. You want to call it red beryl, you want to call it Bixbyte, you want to call it red emerald. Trust me, I know what you're talking about, and most everybody does. So
good. Well, we've had a very interesting program so far, and I'm sorry for the complications that meant some people didn't get to join us with that. But I wanted to, first of all, thank all the speakers here. Presentations were well put together and well organized, and I really appreciate it. I'm sure our audience did too. We need also to thank Jolian for his work in the background. But I have a question for Jolian I'd like to answer for everybody. Jolian, can you tell us how many of the previous programs are now available on gem.org and YouTube?
Okay, sure. At the moment, the first 2 are available. I was hoping to get more up this week, but it takes quite a while to encode them and upload. Hopefully over the next, we will have the rest of them uploaded as well. So if you go to gem.org /zoom.php, or if you just go to gem.org, link there for GemQuest at the top, and that will go to the page which will contain all the links for the forthcoming meetings as well. So as soon as we confirm the dates for the April meeting, which probably 25th of April, but
it'll be April 25th.
Yeah,
we're trying to do these all on the last Sunday of each month.
Yeah, that's great. So what I'll do is I'll put that presentation on, and I will double check with Ray to make sure we get the right Zoom start time this time. And then what will happen is you'll see on there the links. In fact, what I'll do, I'll just quickly, so you can have a look, and I'll show you where it's all at.
While you're looking for that, I'd add that the next program in April 25th will be on the quartz family of gems, which would of course be amethyst and all its brothers and sisters, but would not be in the cryptocrystalline agates and so forth. It's just going to be the facetable members of the quartz family. So,
okay, so that didn't work. Let's try again. And share. Are you seeing anything?
We're seeing gem.org.
Good. So you should then see gem, and within here, okay, ignore that. And then here we have the list of episodes. So at the moment we've got the first 2 with video, and as I get time, I'll put the next this week, and probably this one as well will come up this week. And then episode 6, we will have the link for and the information subsequently put down there.
Yeah, and if you could send that link to me on an email, that'd be great.
Okay, will do.
Okay, so unless anybody has any good questions, and I'm hoping someone does, we've had a really interesting, informative program today, and I thank everybody for coming, giving up some time on a Sunday to join us. Thank you, Jolian, for hosting.
I do have one thing just to discuss.
Oh, yeah, go ahead.
And that's going right back to the beginning, and that was the issue of the Tajik yellow beryls. And certainly as far as we're concerned on Mindat, we have flagged that up as these are fraudulent. As there has been absolutely zero hard evidence to say that there is any real gem quality yellow beryl coming from the region. Name itself that was given to the locality is a Russian name, which makes no sense because absolutely no one in Russia believes that it's genuine. If you talk to any of the Russian mineralogists, they all claim that there's absolutely no chance that this is a legitimate find. And there are people who have scoured the country and it's just not happening. And as we know, I mean, we have not only are there things which are suspiciously like the beryls from Afghanistan, you also have the Pakistan, sorry, you also have the Chinese flat Pingwu style beryls as well that have been irradiated with the classic Chinese matrix. The story I heard about this is that this dates back to the 1980s potentially, when an importer of gem material in the US sent a batch of low-grade aquamarine to get irradiated to make it a deeper color for sale, and then got a message back from the irradiation lab saying, "Oh, terribly sorry, something's gone horribly wrong, it's all gone yellow." And that apparently was the start of that. So this was late 80s. I believe that these things, were first reported maybe late 90s or early 2000s as specimens. But yeah, I mean, the story appears to be completely fraudulent from everything that I can gather on.
Well, we've seen similar things going on with topaz, and we'll talk about that when we do our topaz meeting. But any other responses to Jolien's comment, Peter or Clemens?
I have a question for Seth. Am I muted?
No, you're not.
I hear
We can
you.
hear you.
Okay, yeah. I have two specimens of red beryl or red tourmaline.
No, not red.
One one's tabular, it's hexagonal tabular, but it says it's included with pseudobrookite. Is there a lot of pseudobrookite inclusions in red beryl?
Not at the Wawa Mountains, but at Topaz Mountain, yeah, there is pseudobrookite, and you often see the needles inside gemmier crystals where you can actually see through them.
Yeah, I don't see them in here at all. It's tabular, but it says it's from Juab County in the Thomas Range. Is that in Utah?
There are two localities in Utah where you can find it, but only the Wawa Mountains is prismatic and gem quality. The Topaz Mountain in Juab County is where you find the tabular crystals.
Okay, yeah, this is tabular, and that's the one from the Wawa Mountains. I don't know if you can see it. It's it's not bad though. It's
nice.
It's double terminated, and it's sitting right on top of there. There's another one inside here, but I haven't cleaned it out enough. So, I kind of like it this way anyway. The other one would probably deter from this one sitting on the top. So, anyway, that was my question about the pseudobrookite, but that's not from the same mine. You have your mines at the Wawa range or mountains.
Yeah, the Wawa Mountains are in Beaver County, which is kind of next door. But like I said, they haven't found any gem quality on Topaz Mountain, and they haven't cut any gemstones from Topaz Mountain.
There's a lot of topaz there. I remember I bought a bunch and sent it to Singapore back in early 80s. So, but I have been to Artai as well. And wow, what a place that is. I've got this double double Japanese twin shoral tourmaline, and it's like 6 inches by 6 inches. It's just like, oh, it's just beautiful. I picked that up in Artai, and a lot of other barrel there as well, which were, because they have a lot of huge crystals in Artai in the mountains as well. So it's a beautiful place. It was quite the trip. So
Thanks so much for the question, Bert. I really appreciate it. Any other questions, anybody?
Yeah, I have another question for Thess, going more or less in the same direction. There are very rarely specimens of red beryl in combination with topaz. So from the violet claims there is no topaz, if I'm right. They are all from Topaz Mountain?
The Wawa claims also the beryl grows in what they call a topaz rhyolite. But like I said, I spent about a week there mining, and I did not find a single specimen or any topaz, you know, in any appreciable quantity that that you could really call a specimen. So I really think that it's only Topaz Mountain where you'll find the topaz specimen. I don't know if they occur in like microscopic quantities, because the rhyolite does have a, you know, kind of a sparkling appearance, but it's nothing in any appreciable size. No.
Yeah, I'm not a micromount collector. I just want to see the specimens I have with my bare eyes.
Right.
Okay, thanks.
Although I will say that in at the Wawas, they don't have topaz, but one of the things they do have is they have highlight or opal specimens that you can collect that are like botryoidal, I guess is how you pronounce it, the habit.
Yeah, that's what highlight usually forms in sort of a crusted botryoidal. Any other questions at all for anybody? Because we've had a good run tonight. And thank you for those in Europe who are up extra late, and particularly our two speakers. And thank you everyone else for coming. And I'd like to invite you to come to the next meeting on April 25th at 3 p.m. Eastern, noon in Pacific time, and 8 p.m. Greenwich in London time. And hopefully Zoom and everybody will get the times all jived up correctly next time. So we'll have everybody able to come. So if you have friends that are really interested in quartz, this next meeting is going to be the one. So I'm looking forward to that. Then the one after that in May will be on emeralds. So we'll get a chance to really talk about emeralds. Thank you so much. And I'd like to bring this meeting to a close. Thank you, Jolion. Thank you, speakers. And especially thank you, audience.